Okay, hi guys. I'm recording these slides so you can watch them kind of in place or an alternative to us being in class together tomorrow on Monday the 19th. So I'm going to go through the slides and talk about them as I usually would. And I'm also going to read some segments of the book to try to help illustrate the topics I'm talking about. I do seem to have a little bit of a cold. My nose is kind of stuffy, so if I sound weird, I apologize. Hopefully you can understand me okay. Okay, so this is part 2 of chapter 6, Thinking as Hypothesis Testing. Do you believe that children who are neglected become teenage delinquents? Does jogging relieve depression? Will a diet that is low in fat increase longevity? Do clothes make the man? Will strong spiritual beliefs give you peace of mind? Does critical thinking instruction improve how you think outside the classroom? So all of these questions concern a causal relationship. And what I mean by causal is that one variable, so for example, neglect, is believed to cause another variable. For example, delinquency. So what sort of information do we need to determine the truth of causal relationships? So stop and think for a minute about the way you would go about deciding if neglecting children causes them to become delinquent when they're teenagers. You could decide to conduct a long-term study in which you would divide children into groups, so telling some of their parents to cater to their every need, others to neglect them occasionally, and then still others to neglect their children totally. You could require everyone to remain in these groups, right? So you have the three. One, they catered all the needs. One, they neglect them occasionally. The other, completely neglected. And you could have them stay in those groups until they reach their teenage years, at which time you count up the number of children in each group who became delinquents, right? So remember, of course, that you would then have to define operationally the term delinquent, what counts as being delinquent. But then this would make a good way of deciding whether neglect causes delinquency. But of course, it's completely unrealistic. It would be good because this method would allow you to control how much neglect each child received and isolate the cause of delinquency, which would be a systematic way of seeing whether the differences in each group is due to how they were treated. However, it's really unrealistic and it's pretty ludicrous, actually, because very few people would comply with your request to cater to or neglect their children, right? It's not ethical. We can't ask people to engage in potentially harmful behaviors. So in some experimental settings, it is possible to isolate and control the variables that interest you to this kind of extent. If you wanted to know if grading students for coursework will make college students work harder and therefore learn more, you could randomly assign college students to different grading conditions. Half the students could be graded as pass or fail without receiving letter grades, and the other half would receive traditional letter grades, A, B, C, D, F. At the end of the semester, all students would take the same final exam. If the average final exam score of the students who received the grades A, B, C, D, F were statistically significantly higher than the students in the pass-fail condition, we could conclude that grades do result in greater learning, right? And we're going to talk more about this idea of statistical significance in the next chapter, chapter 7. So, given the constraint that you cannot tell parents to neglect their children, how do you go about deciding if child neglect causes delinquency? So you could decide to find a group of parents and ask each about the amount of care he or she gives to each child. Suppose you found that in general, the more the children are neglected, the more likely they are to become teenage delinquents. Because you lost control over your variables by not assigning parents to catering and neglecting groups, it's not possible on the basis of this experiment alone to conclude that neglect directly causes delinquency. It is possible that parents who neglect their children differ from caring parents in other ways. So parents who tend to neglect their children may also encourage drug use or engage in other lifestyle choices and activities that contribute to the development of teenage delinquency. So a point that's made in several places in our book is that just because two variables occur together, in this example, neglect and delinquency, it does not necessarily mean that one caused the other to occur. So this is our first area that we're going to be talking about in terms of this set of slides is how do we determine cause, right? So if we can directly control those variables and manipulate those variables, that's one way. That's the best way of systematically working with them to determine cause. But if you can't do that, what do we do? Right. So with determining cause, we have this idea of the three-stage experimental design. Right? So when researchers want to be able to make strong causal claims, one thing causes another, they use a three-stage experimental design. An experimental design is a plan for how observations will be made. So we're going to break down experimental design to the basics of 3 stages. So stage 1. The first stage involves creating different groups that are going to be studied. So in the example about the effect of pass-fail grading on how much is learned, the 2 groups would be those who receive a letter grade and those who receive a grade of either pass or fail. Okay. So those are our 2 groups. It's important that our 2 groups differ systematically only on this particular dimension. So we don't want all the students in the letter grade group being taught by Professor Long-Winded, while those in the pass-fail group are all taught by Professor Mumbles, right? So one professor may be a better teacher, and students may learn better because they have that instructor, and it has nothing to do with the way that they're being graded. And so this is what we talked about last time as a confounding variable. The fact that they have a different instructor who may be better confounds our study so that we can't determine, if it's an actual causal relationship between what we're manipulating and our outcome variable, our dependent variable. So one way to avoid this confound is to assign half of the students in each class to each grading condition, with the assignment of students to either group done at random, right? So random assignment. We talked about random selection of participants. Now that's important to experimental design. Now we're talking about random assignment. And so the difference there is that random selection is when we are selecting from our population who is going to be in our study. Random assignment is, okay, now that we have our group of participants, our sample selected, who gets put into which group, right? Who gets put into the treatment group where they're getting some sort of treatment, and who's getting put into the control group where they're not getting the treatment. So random assignment ensures that any individual differences or motivational characteristics show up in equivalent proportions in both groups. So what that means is that if we start with our overall sample of participants, and then we use some random method to assign half to one group and half to the other, we would expect any particular individual characteristics that may confound our study to be randomly assigned to be equal in both groups, right? If we're randomly assigning, we're not doing it so that half of the group has one particular characteristic that we're not studying and the other has a different characteristic, right? This is a way of trying to ensure that they get evenly spread out between the 2 groups. So for example, going back to our Sesame Street example from last time, when we're assigning children to our Sesame Street and no Sesame Street groups, we don't want the ones in one group to be older, wealthier, healthier, more motivated, maybe less diverse, etc. than the other group. We would want them to be approximately the same on each of these characteristics. So now that we have from stage 1 our 2 groups and we've randomly assigned our participants to our 2 groups, our control and treatment, and I keep saying two groups. It's not necessarily two groups, right? We can have more than two groups. But for these examples and for simplicity of right now, we'll just talk about it in terms of two groups, treatment versus no treatment. So once we have our groups, then we go about doing our experiment, right? So the second stage involves the application of the experimental treatment. So if we're conducting, for example, a drug study, then one group gets the drug and the other group does not get the drug. So usually in this type of study, the non-drug group doesn't just not get anything, they get what we call a placebo, which is something that is like a sugar pill, or basically something so that they don't know they're not getting anything, but really it's not the thing we're studying, right? And we'll talk more about that later. So usually they would get a placebo, which would look and or taste like the drug, but doesn't actually have any drug in it. And so the reason for this is so that we avoid any effects of the subject's beliefs or expectancies on the outcome. Okay. So in the Sesame Street study, when we get to stage 2, we have, randomly assigned our kids to be in the two groups. Now we do the treatment, right? So we expose one group, the treatment group, to the show for a certain number of hours or a certain number of days, and then the control group doesn't get exposed to those things. So measurement of our dependent variable, the control group, allows us to rule out any normal fluctuations in the DV that might have occurred in the absence of treatment. So basically, we give them nothing or some sort of placebo, and then we measure what happens. And even if there is somewhat of a change in our dependent variable, so for example, their vocabulary is a little better afterwards, we can control for that change that naturally occurs or occurs because of whatever placebo effect when we look at the group that actually received the treatment. Okay? So we prevent the placebo effect. In this case, we may do that by having a third group watch some other non-educational children's program. Right? So we have one group that watches Sesame Street, one group that maybe doesn't watch anything, and then a third group that watches something, but it's not an educational program, right? It's some other children's program. And then so we can see the effect of no TV. How does that affect their vocabulary? Some TV, but not educational, not Sesame Street. How does that affect their vocabulary? And then third, the actual effect that we're interested in. Does watching Sesame Street increase their vocabulary? Okay. So again, the placebo effect is the influence of expecting something to happen, right? So in our little cartoon here, dude, I feel so drunk. The guy says, but you're only drinking non-alcoholic beer. Stop it, you're ruining my placebo effect, right? So if you are drinking beer and you don't know that it's non-alcoholic beer, then maybe you still feel like you catch a buzz because you're like, yeah, I'm drinking beer. I should feel buzzed right now, even though there's no alcohol in it. Okay, now stage 3 is when we actually evaluate our results. So evaluation is our final phase, and measurements are taken, and the two or more groups are compared to see how they did on the outcome measure. So for example, with the Sesame Street one, how do the vocabulary tests compare between our different groups? In the example from the book, in the grading example, then at this point, this is when you're comparing the final exam scores for the students in the letter grade group versus the students in the pass-fail group. Okay? So stage 1, establish your groups. We have our sample, randomly allocate them to be in our different groups. Stage 2, do whatever it is that you're studying, right? Do the treatment. And stage 3, look at the outcome and compare the outcome between our groups. So if students in the graded group perform significantly better than the students in the pass-fail group, then we would have a strong support for the claim that one grading method caused students to study harder and learn more than the other. Or in the case of Sesame Street, if the kids who watched Sesame Street had really big gains in their vocabulary compared to the kids who either didn't watch anything or kids who watched a non-educational kids show, then that would be pretty strong evidence to say, look, Sesame Street has a great effect on vocabulary. So again, if the groups were the same to begin with, and we hope that by using random allocation, they should be, and the Sesame Street group performs significantly better, then we can infer that watching Sesame Street has a causal influence on kids' vocabulary scores. So determine causal and effect relationships, we have to isolate causal variables and control other potentially influential variables, which we know as confounds or confounding variables, right? So this goes back to what we talked about at the very beginning. How do we determine if one thing caused another? Well, we do that by isolating the variable we think is causing something to happen, and we control for other things that may influence the outcome that aren't the thing we're interested in. Again, just to reiterate, random assignment of participants to groups creates those equivalent groups. So we're starting at equal, and so the individual differences or other characteristics are distributed equally to our different groups. And that way they're not all stacked in one group and could affect, what it is that we're studying. They could get in the way of seeing the effect of the causal variable or the independent variable. Okay, so another example. Let's say you're studying learning in rats, right? And you do this by observing how quickly they learn a maze if they're rewarded. So we all know this kind of idea of, you stick a rat in a maze and there's some cheese on the other side. So you study how fast does this rat learn the maze. If you put them in the maze over and over, how quickly can they learn it? Because obviously the rat wants to get to the cheese. So you could rig your groups so that Speedy and Flash, your fast rats, are in the cheese group, right? And Slowpoke and Sleepy, your slow rats, are in your no cheese group. So this is basically saying that we're not starting at equal, right? If you put all your fast rats in the reward group and your slow rats in the no reward group, then probably, your fast rats are going to learn faster, right? So how do we know that it was the effect of the reward, the cheese, versus they were just the fast rats in general, right? We don't have that guarantee. We can't determine cause because the confounding variable there is the fast rats were in one group and the slow rats were in the other. So this is the whole point of random assignment. If we randomly assign them to groups, then all the rats are equally likely to be in either group. So all the fast rats are equally likely to be in the reward versus no reward group, and the slow rats are equally likely to be in the two groups. So then if they're equally likely to be in either group, we can expect that the fast rats and the slow rats should show up in equal proportions in both of our groups. Therefore, kind of starting us at level. So we can really see what is the effect of the cheese, not the effect of whether we stuck the fast rats or the slow rats in a group. Okay, so retrospective research, retrospective experiments look back in time to understand the causes for later events. Okay, so these are about looking backwards. There are many problems associated with this sort of research. Okay? So one way to think about this is retrospective. You think of retro, right, which means old school or like something from the past. So when you're doing retrospective research, you're looking in the past and trying to use information from the past, like memories, to try to understand what's going on currently. So there are issues with that because, as we talked about in the memory chapter, memories are pretty bad a lot of the times, right? They're very selective and very malleable. They can be changed easily. You think you remember something, and really when there's like actual proof, it's totally different from what you remember. So retrospective research, retro research, looking in the past, has a lot of issues. A better method for understanding causative relationships is prospective research. And prospective research is a method of conducting research in which possible causative factors of an event are identified before the event occurs. So what this means is you identify the things you think are going to have an effect, and you record them, and then you basically wait it out and you look to the future, you look forward in time to see if what you hypothesized occurs, right? So maybe you think that certain lifestyle factors affect whether somebody is likely to get cancer. So instead of saying, okay, you have cancer, let's think back, how many cigarettes did you used to smoke? How many, I don't know, how many drinks did you have per week? How stressed were you? Right? So instead of finding somebody with that characteristic now and trying to have them remember the past with retrospective research, instead you measure those things in your group right now. How many drinks do you have a week? How many packs of cigarettes do you smoke a week? How stressful are you? All those things that you think may affect whether somebody develops cancer, you record them right now when you can be sure that you're recording accurately. And then you wait and you see who gets cancer, right? Maybe you wait 5 years and you know, okay, well, this group of people who had cancer, we recorded they had these characteristics, and this group that didn't develop cancer, we recorded they had this characteristics, and then you can compare and you know that the data are accurate because you're the one who wrote it down, recorded it somehow. You're not asking people to just try to remember the past. Okay. So going back to this idea of retrospective versus prospective research, most of the research we conduct as intuitive scientists is retrospective, right? That kind of poorer method of research. We often seek explanations for events after they have already occurred, right? So a lot of times we're not planning towards the future where something happens and we go, I wonder why that happened. So how many times have you tried to understand why like a seemingly angelic child committed a serious crime, or why maybe somebody who was a star rookie seems to be losing his touch? Like all of a sudden he was great and now he's not so great. Or maybe how a political underdog won their, political contest. So a lot of times it's something happens and then we look backwards to see why did this happen. But the better method of research is to record things as they are that we think will have an effect and then see how it plays out. Okay. And a lot of that is because our retrospective attempts at explanations are biased by our selective memories and our lack of systematic observations. We're not being systematic in recording things. Now, something that's related to, but isn't the same as determining cause, is this idea of correlation or correlated variables. Okay. So correlated variables are two or more variables that are related to each other. When variables are positively correlated with each other, that means that as one increases, the other also increases. And I think I have this on 2 slides here. So correlated means they're related. And if they're positively correlated, that as one goes up, the other goes up. And if one goes down, the other goes down, right? So they move in the same direction, then they're positively correlated. So for example, age and number of wrinkles. The older a person is, the higher the age is, the higher the number of wrinkles they tend to have. Same thing with weightlifting sessions and muscle mass. The more weightlifting sessions you have, the higher the muscle mass. Or vice versa. The fewer weightlifting sessions, right, like me, the lower the muscle mass. So those things are positively correlated because as one goes up, the other goes down, or as one goes, as one goes up, the other goes up, or as one goes down, the other goes down. My brain was getting ahead of me. Okay. Now we can also have negatively correlated variables. So this is where they move in opposite directions. Positively correlated, they move together, up and up, down and down. Negatively correlated, they're in opposite directions, which means that as one increases, the other decreases. So for example, hours of cardiovascular exercise and percent body fat. So you would expect that the more hours of cardiovascular exercise somebody participates in, the lower their body fat is, right? So opposites. Higher hours equals lower body fat. Or maybe a more kind of direct one, the number of times you mow the lawn, let's say in a week, and the length of the grass. Well, if you're mowing your lawn every day, so a high frequency of mowing the lawn, your grass is going to be really short, right? It's never going to get very long. So the higher number of times you mow the lawn, the shorter your grass is. Or the lower number of times you mow the lawn, maybe you don't mow the lawn, then the grass gets taller. So high mowing is associated with low short grass, and low mowing is associated with high tall grass. Okay. And you can see in these graphs here, with positive correlation here, you can see as one variable on the x-axis gets higher, the other variable on the y-axis also gets higher. And so we see this direction of up to the right indicates a positive correlation, and down to the right indicates a negative correlation. Okay, so as x is getting higher, y is getting lower. So some examples of correlation. The IQ of identical twins. Identical twins share the same DNA, right? They started as one sperm and one egg combined, and then that split. So they have the exact DNA, so you would expect them to have at least very similar IQs, right? So as the IQ of, if you measure the IQ of one twin, the other ones should be pretty similar. So that's a positive correlation. Now the correlation between absences and grades is a negative one. Typically, the fewer times somebody comes to class, right? So the more absences they have, the lower their grade is. Okay, so if somebody misses almost every class, you would probably expect their grade would tend to be pretty low, versus somebody who comes to class all the time would tend to have a higher grade, right? So if they have no absences or very few absences, they have a higher grade. Now, sometimes correlations are not super intuitive, right? So we have an example of ice cream sales and the number of shark attacks on swimmers. Okay. So the first two examples that we use here, IQ and absences and grades, you can kind of see the causal factor underlying it, right? So the causal factor of a positive correlation in the IQ of identical twins is that they started as one, fertilized egg, right? The causal factor in terms of absences and grades is, well, if you miss a lot of class, you're probably missing a lot of the content, and therefore your grades are lower, right? But the issue with correlation is we don't know for sure, just because two things are correlated with each other, that one is causing the other. And that is definitely clear in this third example. So ice cream sales, how much ice cream gets sold, is positively correlated with the number of shark attacks on swimmers. Now, this doesn't mean that sharks only like to eat people who are eating ice cream, right? Maybe ice cream sales grow up, and then this means lots of people are eating ice cream, and then they go in the ocean, and then sharks only want to eat the people who eat ice cream, right? they're both related to heat. When it's hot out, people tend to buy more ice cream. Ice cream sales go up. And when it's hot out, people tend to go in the ocean, right? You don't go in the ocean in February usually. You go in the hot months, in the summer months. The summer months, there tend to be lots of high ice cream sales because people are hot, they're buying ice cream. There are also more people in the ocean, and therefore the sharks have a lot more people to eat, right? So it's not that ice cream sales directly influences shark attacks or vice versa. It's both of these factors are related to heat. Heat increases ice cream sales, and heat increases the number of people in the ocean, therefore leading to more shark attacks. So people frequently confuse correlation with causation. But just because two things occur together doesn't mean that one causes the other to happen. So, for example, just because a parent has a high IQ or high intelligence and child has high IQ or intelligence, right? So although parents and children's intelligence are positively correlated, this is something they found in studies, we can't necessarily make the statement, infer that the parents cause their children to be intelligent. Just because parents who are smarter or have higher intelligence tend to have kids who have higher intelligence doesn't mean that one directly caused the other, right? For example, through inheritance. It could be that children affect the intelligence of their parents, right? I guess theoretically, it could be that. Maybe if you have a smarter kid, you have to work harder, to keep up with them, and that increases your intelligence. Or, probably more likely, it is possible that both children's and parents' intelligence are affected by some other third variable. So this is like ice cream and shark attacks. They're not directly related to each other. They're both affected by heat. So maybe the fact that the children and parents are probably growing up in similar circumstances. Maybe they live in areas where there's good nutrition. Maybe they have high socioeconomic status. They have the ability to attend school regularly, or things that lead to kind of the idea of formalized intelligence or IQ. Right? So maybe there are other lifestyle factors that are related to both children's and parents' IQ. It's not that one causes the other, it's just they both happen to grow up in similar circumstances and have the same opportunities, and that leads to, higher intelligence for both of them. So keep in mind, correlation does not imply causation. And if you've taken a stats class, or if you're going to take a stats class or a research methods class, you are going to hear this a lot. That's why there are memes about it, right? I didn't make this meme. This is a meme that exists. Golden rules of respect? No. I thought it was correlation doesn't imply causation. So keep in mind, the question of causation is usually complex, right? Just because two things occur together does not mean one causes the other. Okay. So correlation does not imply causation. Kind of chant that to yourself. Correlation doesn't imply causation. Remember that. It's important. So, the term illusory or illusion, right? Illusory correlation refers to the erroneous belief that two variables are related when in fact they're not related. Okay. So this is something that occurs or happens to professionals and non-professionals. Okay. So for example, clinical psychologists' use of the Rorschach ink blot test, right? So we have all seen that. You have an ink blot and they say, what does this look like to you? Right? This kind of prototypical psychologist thing to do. Right? So clinical psychologists use the Rorschach ink blot test, some of them, and claim it's helpful, even though research shows it's not effective as a therapeutic tool, right? So even though they know there's no research supporting that it's actually useful for anything, they feel it's helpful anyway. So that's this illusory correlation. They feel like two variables are related. I feel like what people say when they see this ink blot reveals something that's going on in their mind. Okay? And illusory correlations are maintained, or they stay in our brain because they're based on confirming instances. So this means that people tend to only remember the things that confirm their belief, right? People don't remember the things that are contrary to their belief. So this gives us this false idea, this false feeling that things are related to each other when really they're not related. So moving on to the ideas of validity and reliability. So the validity of a measure is usually defined as the extent to which the measure measures what you want it to, right? Are you really measuring what you think you're measuring? So a test asking you about the number of phones in your house is not a valid measure of intelligence, right? So if I think I'm measuring intelligence and I go, how many phones do you have? That's not a valid way of measuring that. It's not measuring what I think it's measuring. Now, there are lots of different kind of types of validity. There are lots of different ways of establishing that something is valid and measuring what you want it to. And one of those means is called convergent validity. So when several different measures all converge on the same conclusion, the measures have convergent validity. That means they're all measuring the same thing. And the accuracy of any measure is supported when a different measure of the same thing yields a similar result. So this is something that occurs a lot when people are developing like surveys for measuring psychological constructs, psychological ideas, right? So how do you measure depression? How do you measure anxiety? You can't pull out a measuring tape and, wrap it around somebody's head and go, this person has low depression or this person has high anxiety, right? You can't do that. You need some measure that gets at that construct, that thing you can't physically see and measure. And we want to make sure we're really measuring what we think we're measuring, right? So one way of doing that is if we have like a survey or a tool that we believe accurately measures depression, then if we develop a new one and it gets really similar results to the one that we think is already working, then that implies that the new one is also valid, right? Or if we have lots of different tools that all seem to point to the same conclusion, then those tools have convergent validity. Because they're all seem to be working, then they are all valid because they're all getting to the same conclusion. Now, illusory validity, again, that illusory word, the illusion of validity, refers to the overconfidence in judgments. Right? Let's see here. So, both professionals and non-professionals place great confidence in their conclusions about most life events, even when their confidence is objectively unwarranted, right? So objective versus subjective. Objective means like you can, almost like you can observe it directly. You can measure it. Versus subjective is a feeling, right? So overconfidence in judgments is called illusory validity. You think something's valid, but it's just an illusion. In an experimental investigation of this phenomenon, Oskamp, back in the 60s, found that as clinicians were given more information about patients, they became more confident in the judgments they made about those patients, even though their judgments didn't increase in accuracy. So what's interesting is the result is they were not more accurate in judgment, but they thought they were, right? They were more confident they were right. So why do people place confidence in fallible judgments? And there are several reasons why this happens. And a primary factor is the selective nature of our memory, right? We tend to remember successful judgments and forget unsuccessful ones, right? We tend to remember when we're right and forget when we're wrong. Therefore, we get really confident in our ability to make good judgments because we only remember the good judgments that we made. Okay? So this is what leads to this idea of illusory validity. A second reason for the illusion of validity is the failure to seek or consider disconfirming information. All right, so this kind of goes back to what we've talked about in the past in terms of like confirmation bias, right? We tend to ignore information that is contrary to what we believe, or we tend to not seek out information that's contrary to what we believe. We only want to find evidence for something we think already, right? So this is that idea of we're failing to seek or even consider disconfirming evidence. So these are the primary reasons why people tend to believe that variables are correlated when they're really not correlated. We only seek out evidence that supports our idea that they're correlated, and we only remember those times when they happened together, when it confirms our belief. Now, when you hear about validity, a lot of the time you'll also hear about this idea of reliability. So validity and reliability are two concepts in research that go very hand in hand. So whereas validity is, are we really measuring what we think we are? Reliability is, how consistently are we measuring what we're measuring? So reliability is the consistency with which it measures what it's supposed to measure. So again, we can talk about the validity and reliability of some sort of measuring tool, like a survey or a test. So if it's valid, we're really measuring what we think we are. If it's reliable, that means it gives us consistent results. We expect similar results over and over whenever we use it. So a reliable measurement instrument gives the same or similar results when it's applied repeatedly to the same quantity or quality. And it may be helpful to have an example of this. So for example, if your bathroom scale is reliable, then it gives you a very similar reading when you weigh yourself at 8 a.m. as it does at 8 p.m. You know, maybe your weight fluctuates by a pound or two throughout the day, which is natural as you're drinking fluid, as you're active, whatever, right? But you can expect it to be within a couple pounds. If your scale says that you're 150 pounds at 8 a.m. and 220 pounds at 8 p.m., that's just crazy, right? That's unreliable. You can't count on it because it really depends, you know, which time you're using it. You get a totally different number. So if you get similar or the same results, it's reliable. If it's all over the place, it's unreliable. So researchers in the social and physical sciences devote a lot of time to the issue of reliable measurement. So we say that an intelligence test, for example, is reliable when the same person obtains scores that are in the same general range whenever they take the test, right? So if you took an IQ test today and you got 105 and you took the same IQ test again tomorrow and you get 75, that's an issue. Then that measure is not reliable. So keep in mind that reliability and accuracy are not the same thing. Accuracy is more akin to validity, right? Are you really getting what you think you're getting? So here are some different kind of examples or possibilities here. So on the upper left, we see this method of trying to get to the bullseye is neither accurate nor reliable. It's not accurate because we're not hitting the bullseye, and it's not reliable because the darts are spread all over the place. Now this one on the upper right, this is reliable. We always hit the same general area. It's just not the bullseye. So it's reliable, but it's not accurate. Bottom left, well, this is pretty accurate. We're always hitting around the bullseye. But again, we're not getting to the same area, or the same, tight cluster. So where this is definitely more accurate, we're hitting the bullseye, at least some of the time, or around the bullseye. It's not reliable because we often get different results. Now this last one, this is both reliable and accurate. We're hitting the bullseye, we're hitting what we want to hit, and all the darts are basically in the same area. So we're getting the same result each time, and that result is accurate each time. So some examples. How can you tell if we're talking about validity or reliability? Validity being we're measuring what we want to measure, or we're the accuracy, right? Versus reliability, is it consistent? Do we get similar results? So this example, both eyewitnesses agreed that the blue car ran the red light and hit the gray truck. So this is one way of measuring how something happened, right? Are we talking validity or reliability here? So there are key words that clue you in. Both eyewitnesses agreed that the blue car ran the red light and hit the gray truck. So when we're talking about agreement, we're talking about consistency, right? So when we're talking about agreement, we're talking about reliability. Okay, so you notice that your friends have a consistent account of what happened at the party last night. So maybe this one's a little more obvious, right? Again, keywords clue you in. You notice your friends have a consistent account, right? So it doesn't matter which friend you're asking, you're getting the same account of what happened, the same result. Therefore, we're talking about reliability again. Now, you notice that the temperatures predicted in the weather report are very close to the actual temperatures measured later on that day. So again, keywords, predicted and actual. So what was predicted, what was trying to be measured, was very close to the actual thing, right? We're kind of talking about what? Accuracy here. The predicted weather is very close to the real weather. That means we seem to actually be measuring what we are trying to measure when we're predicting. Therefore, we're talking about validity. The validity of the predicted weather. So think about our candy experiment we did last time, where I think that people who eat dum-dums are dum-dums and people who eat Smarties are Smarties, and that you have, either lower or higher intelligence depending on which one you choose. So think about how I measured the dependent variable of intelligence. First, we had the pre-test with those 10 kind of brain teaser type questions. And then we had a post-test where you saw 20 objects. You had an interference task where you had to count backwards for a minute. And then you had to try to remember those 20 objects. So think about that. Is that a valid way to measure intelligence? I'm claiming that that's how I'm measuring intelligence. That's how I've operationally defined intelligence, is the ability to understand brain teasers and remember things, and actually the difference between them. And some people had questions about this last week, like, what's a good score? Is 0 a good score? Is a high score a good score? Is a low score a good score? We don't know. So is it reliable? Can I likely get the same score for you if I did it again next week? Is it valid? Am I really measuring intelligence? Right? If it's not reliable, if we don't expect to get the same answer next week, then what's wrong with it? If it's not valid, if I don't seem to actually be measuring intelligence, why not? What's wrong with it? How could I improve this? Okay? So there's some things to think about. Now, talking about thinking about things, let's think about errors. Okay. So there are two different ways that we can make errors in any hypothesis testing situation. Because keeping in mind, this whole chapter is about hypothesis testing, right? Either confirming or disconfirming an idea or belief we hold. So to kind of illustrate the two different ways that we can make these errors, let's have an example. So you and your friend go for coffee together every day. And instead of always having to split the check, you decide that you're just going to, you're going to flip a coin, and whoever's, side is picked, they're going to pay that day. You figure coin flips are 50-50, so it should work out to you paying half the time and your friend paying half the time. Okay. So you decide who's going to pay by your friend's flip of a coin. Your friend's flip of a coin. Okay. So the result for the past 9 days has always been tails, which means that you're paying, your friend is not paying. Okay. So every day for 9 days, the coin lands in his favor. He doesn't have to pay. Do you think he's cheating or not? Right. So there are several different possibilities here. So let's look at a chart. So the way this chart is laid out, so on the left is the truth. Either he is, scratch the A, either he is cheating or he's not cheating, right? There's only two possibilities there. Either yes, he's cheating, or no, he's not cheating. So everything listed in the top row of the table is assuming, yeah, he really is cheating. Everything listed in the bottom row of the table is he's not really cheating. Now we have at the top your decision of whether you decide he is or he isn't cheating. So on the left column, you decide he is cheating. And on the right column, you decide, nah, he's not cheating. I've just been super unlucky. Right? So in this first cell, if he is cheating and you decide this guy's cheating, then that's right. You're correct. Okay. Versus down here in the bottom right cell, if he's not cheating and you decide he's not cheating, you're correct. Correct decision, right? So here and here we have correct decisions, but we also can have two different types of errors. Okay. So if he is cheating and you decide he's not, well, you're wrong. That's an error in judgment. But this is kind of the less serious error in judgment, right? So in this case, yeah, he is cheating you. You do have to pay more, but maybe you're not going to ruin a friendship by accusing him of cheating. Right? Versus if he's not really cheating and you say you're cheating, right? This could be an issue. This, maybe your friend gets super pissed off and just never wants to have coffee with you ever again, right? So I guess it kind of depends which you think is more serious. You paying for coffee more than your fair share, or losing a friendship. I think probably losing a friendship would hurt me more. If he was actually not cheating and I'm like, you're cheating, and then he hates me, would be an issue for me. So we have two different ways of making errors. Either he's cheating and you say he's not, or he's not cheating and you say he is. Okay. So these are our 4 possible outcomes for this scenario. And these are the 4 possible outcomes, not exactly, but the same similar kind of thing, as when we're making a decision about a hypothesis, right? So either a hypothesis is true or a hypothesis is not true. And you either decide, oh, yeah, my hypothesis is true, or my hypothesis is not true, right? So we can kind of create an equivalent scenario talking about hypothesis testing as talking about whether your friend's cheating on buying coffee or not. Okay. So there are 2 different ways that you can make errors in any hypothesis testing situation. But these 2 different errors are not equally bad. Like here, right? It's not equally bad to accuse him of cheating when he's not, as it is to not accuse when he is. So you need to consider the relative badness of different errors when you're testing a hypothesis. Okay, which one is the more serious error? Which one is worse? Which one's more bad? Okay? So if you take a course in statistics or experimental design, you'll find that the idea of error badness is handled by requiring different levels of confidence for different decisions. So the need to consider different types of errors is found in a lot of contexts. Not just if your friend is cheating on buying coffee or if you're testing a hypothesis, but just like all around us, we make decisions. So a basic principle of our legal system is that we have to be very certain that someone has committed a crime. We have to be beyond a reasonable doubt before we can convict that person. By contrast, we don't have to be convinced beyond a reasonable doubt that she's innocent, because wrongly deciding that someone is innocent is considered less severe than wrongly deciding that someone is guilty. So here we have the same kind of 2-by-2, right, situation. So either they really are innocent or they really are guilty, and the verdict can either be guilty or not guilty. So if they're really innocent and they're found guilty, that's really serious, right? We're sending an innocent person to jail. Versus if they are guilty and we don't find them guilty, we're not certain beyond a reasonable doubt, then we're letting a guilty person off. So most people would think that a wrongful conviction is a more serious error than a wrong acquittal. Okay, so we don't have to be convinced beyond a reasonable doubt that someone is innocent, because wrongly deciding that someone is innocent is considered a less severe error than wrongly deciding someone is guilty. So similarly, when we're testing hypotheses, you need to be aware of the severity of different types of errors. So before you decide, for example, that no matter how hard you study, you'll never pass some course, or the medicine you're taking is or is not making you better, you need to think about what are the consequences of if you're right versus if you're wrong, right? So if you're thinking, oh, no matter how hard I study, I'm never going to pass. Well, what are the consequences if you're wrong? And if you did put in the time to study, then you would pass, right? So what's the consequence? Not passing a class. You have to decide how severe is that to you. Or talking about medicine, if we're talking about taking a medication, if you think that the medication is or isn't going to make you better, you really have to weigh up the idea of, well, what happens if I'm wrong, right? If you think the medicine isn't going to make you better, so you don't take it, what's at stake if you're wrong there? So some decisions require you should be more certain about being correct than others. Some are a lot more serious than others. Now, just as a kind of follow-up, so when we talk about the two different types of errors you can make, we literally call them type 1 and type 2. Type 1 is the more severe error. Type 2 is the less severe error. So what these are will kind of change depending on what situation you're in, like we talked about, and which one's more serious. But just remember, type 1 is saying you found an effect or you found somebody guilty when they're not. So you find something to be true when it's not. And type 2 generally is you find something to be not true when it is. Okay. So some examples. So false positive or type 1 error would be a doctor telling a man, you're pregnant. So he's mistakenly finding a baby when there is no baby. So that's equivalent to finding an effect when there's no effect, or finding that your friend is cheating on coffee when he's not cheating on coffee. Okay. Versus type 2 error in this case would be a woman who is very, technically you can't be very pregnant or not very pregnant, right? But she's very pregnant. And the doctor says you're not pregnant. So there is a baby there, and they're missing the baby. They're missing the effect. Okay. So type 1, type 2. Or another way to remember it, I like this example. Type 1 error is like Shawshank Redemption. Okay. So hopefully you guys are old enough and have seen Shawshank Redemption and are old enough and know what's up with O.J. Simpson. So type 1 error, Andy Dufresne is convicted of killing his wife and her lover when he didn't do it. Spoiler. Sorry. Should have said that first. Spoiler alert. Right? So he's convicted and he spends a bunch of time in this prison called Shawshank. That's the whole premise of the movie. Okay. So type 1 error, Andy Dufresne found guilty, not guilty. Pretty serious. He spends his life in prison. Type 2 error is like O.J. Simpson and the murder of Nicole Brown Simpson. And I feel bad, but I forget the name of her friend who died also. So this was a huge case in the 90s. I remember being like in 4th grade when the verdict came down. And a lot of people really, really, really think O.J. Simpson did it. That he murdered his wife and her friend, but he didn't get convicted. Right? So there's this very famous kind of situation where they said, oh, we found this glove at the crime scene. He says, that's not my glove. That wouldn't fit. My hands are too big. And he does this whole show in the courtroom where he's like, oh, it can't fit. My hand's too big. And they came up with this slogan, the defense, if the glove doesn't fit, you must acquit. And so OJ was found not guilty, at least in the criminal trial. In the civil trial, I think he was found guilty and had to pay the family's money. So he was found not guilty in the criminal trial. He was acquitted. So hypothetically, a guilty person was let off. And part of the reason why so many people still think he's guilty is because after the fact, he wrote a book called, like, If I Did It. So the whole premise of this book is, okay, but if I did kill them, this is what I did. So a lot of people see that as kind of he can't be tried again, right? He was already acquitted because of double jeopardy. You can't try somebody again. So he wrote this book, like, but if I had killed them, right? So a lot of people are like, oh, this guy is super guilty. He just got off, right? So what's more serious, sending an innocent man away for life, or even more serious, sending an innocent man to the death penalty, right? So it's a death row, and killing an innocent man, or letting a guilty guy go free. Which one do you think is more serious? Typically, in the American system, we consider falsely imprisoning or sending someone to death row much more serious than letting a guilty person go free. Okay. All right, self-fulfilling prophecies. So we're getting towards the end here, guys. Okay. So the term self-fulfilling prophecy refers to the tendency to act in ways that lead us to find what we expect to find. Okay. So this kind of goes back to something that I mentioned earlier with the rats in the maze. Okay. So in a classic set of experiments, Robert Rosenthal, a well-known psychologist, and his colleagues had their students train rats to run through mazes as part of a standard course in experimental psychology. Half of the students were told that they had rats that had been specially bred to be smart at learning their way through mazes, while the other half of the students were told they had rats that had been especially bred to be dumb at this task. So as you probably can expect, the students with the bright rats had them outperforming the dull rats in a very short period of time. Okay? The results are especially interesting, however, because there was no real difference between the two groups of rats. One group was not specifically, bred to be smart and the other one dumb. There's no difference. They just told one group of students, these are really smart rats, and they told the other group of students, these are really dumb rats, right? So Rosenthal and Fode lied about the rats being specially bred. All the rats were the usual laboratory variety. they had been assigned at random to either group. So if there were no real differences between groups of rats, how do we explain the fact that students who believed they had been given smart rats had them learn the maze faster than the other group? Right? If there's no real difference, how come then there was a difference in how they performed? So this is where that term self-fulfilling prophecy comes in. And so self-fulfilling prophecy has been coined as the term or the label for the tendency to act in a way that leads us to find what we expect to find. Right? If you think that you're smart, you're more likely to perform well on things that you think indicate you're smart. And conversely, sadly, if you think you're dumb, then you're probably more likely to perform poorly on those things. It's a self-fulfilling prophecy. Whatever you tend to believe, then subconsciously you act in a way that confirms that belief, right? So believe you're smart. You're more likely to do better that way, okay? And I believe you guys are smart too. So one way of eliminating the effects of self-fulfilling prophecies is with double-blind procedures or double-blind studies. So what that means is, so if we have a single-blind study, that means that the participants in the study don't know what group they're in, right? They don't know if they're getting medication or if they're getting a placebo. However, maybe the person running the study, the doctors, are like, oh, this medicine is totally going to work. And so if they know that one group is getting the medicine and they know who those people are, maybe subconsciously they're treating them differently than the people they know are receiving the placebo. And that way they're helping those people get better. It's not necessarily at that point that the medication really is working, but the fact that they believe it is working is influencing how they treat them and causing them to do better, just like with the rats in the maze. So one way of getting rid of this self-fulfilling prophecy thing is double blind. If neither the participant knows if they're in the medication or placebo group, and the scientist doesn't know if an individual is in the medication or placebo group, then they treat everybody the same because they don't know who is who. And you may be wondering, well, how do they know if it worked if nobody knows who's taking what? Well, they have special ways of assigning them. Maybe a third party has like a file, a database somewhere that says who is who. But when the doctors are interacting with the patients, they don't know which group they're in. So that's what we mean by double blind. They don't know when they're interacting with people which group they're in, and therefore they're not treating them specially. Now, finally, right, how do we think as an intuitive scientist? So there are some ways of working to make sure that you are everyday thinking. So one theme throughout this entire chapter really is that everyday thinking has a lot in common with the research methods that are used by scientists when they're investigating phenomena in their academic domains, right? So the way we think every day has a lot of stuff in common with how scientists think. A lot of the pitfalls and problems that plague scientists are also very common in our everyday thinking. So if you understand and avoid some of these problems, you're going to be a better consumer of research and a better intuitive scientist. You're going to be making better decisions. So when you're evaluating the research claims of others, or when you're asserting your own claims, your own beliefs, there are several questions to keep in mind to help you. So one, what was the nature of the sample? So think back to our law of large numbers, law of small numbers. And think back to biased samples versus unbiased samples. So what's the nature of the sample? Is it really representative? Is it large enough? Is it biased in some way? What are the variables? How are they operationally defined? What do those terms mean? Do they make sense? And related to that, were the measures sensitive, valid, and reliable? Are they, precise enough to measure what we think we're going to measure? Are they really measuring what we want to measure, and how reliable are they? Are we going to get consistent results? Are the appropriate comparisons being made to support the claims? You may also ask yourself, were extraneous or other variables controlled for? What are some other plausible explanations for this particular result? Does it make sense that something else is actually at play here and we're not really measuring the cause of something we think we are? Do the conclusions follow from the observations? Does it make sense? You know, if you observe some things, does that conclusion make sense? Are correlations, this is a big one, are correlations being used to make causal arguments? Is somebody saying these two things occur together, therefore one causes the other? Because again, that's something that intuitively people think, but a lot of the times is wrong. Okay, so you have to be very careful when you hear claims about cause when really things are just correlated. That doesn't mean that one thing causes another. It could be something totally different going on. Is disconfirming evidence being considered? Are they considering what evidence is contrary to what they think? Right? If they're not really doing a good job of evaluating your evidence. And how could the experimenters' expectancies be biasing the results? Is it a single blind study and therefore they may be treating their patients differently in the experimental group than in the control group? You know, is there some sort of self-fulfilling prophecy going on? Do people who think they're more intelligent outperform the others just because they think they're more intelligent? How are these different things related to that affecting our results? Could they be biasing things? So these are all kind of guidelines to use as you're assessing research or as you're evaluating your own thoughts and you're trying to make sense of the world. Right? So with that, it's the end of the slideshow. So you guys, I have posted, or sorry, I am about to post. By the time you watch this, I will have posted an assignment for you to complete. So this is the equivalent to what I would have you guys do in class, since we're having virtual class this week, or this Monday. So I want you guys to complete the assignment that's called Chapter 6 assignment. And in it, you're going to have to think about identifying some independent variables and dependent variables. You're going to have to think about whether some things seem to be positively or negatively correlated. And thinking about, in terms of like designing a research study, what's your control group and what's your treatment group, right? So you're going to have to do some thinking, some formal research methods type thinking, like you want to, evaluate some claims or you want to test your hypotheses. So that's going to be on Blackboard. That's called the Chapter 6 assignment. I'm also, because we're wrapping up Chapter 6, going to post the crossword puzzle for Chapter 6. So the assignment is required. You're going to get credit as if you had completed it in class. The crossword puzzle, totally not required. That's just for you guys to work on, to test your own knowledge, to see how you're doing, how much you remember from the Chapter 6 that hopefully you are reading along with my slides, or how much you remember from class. And again, you may see some of those clues show up on the next test. So I really recommend that you give it a shot, find out where you are weak in terms of content, and go back and re-review that information. Okay? Use it to guide your studying time. So with that, remember, we are having virtual class on Monday the 19th. I will be available from 5 p.m. to 7 p.m. on Zoom. I'll just be on there if you have questions about the assignment, if you have questions about the content of this chapter or Chapter 5 or really anything at all. Come on there. I'll be hanging out. Ask me your questions, and I will see you back in class in person on Wednesday the 21st at the regular time. Okay? If you have any questions before then, send me an email. Or if you can't, for whatever reason, even though it overlaps with our class time, if you can't make it online for the Zoom thing, send me your email with the questions and I'll answer them on Zoom, or I'll respond via email. I'll post it on Blackboard. I'll get back to you somehow. Okay? So any questions, check in with me. Do the Chapter 6 assignment. I recommend you do the crossword, but it's not required. And I'll see you on Wednesday.